Next speaker is Tomoyuki Yamakami. The title is the last one. The title is Unambiguous and Co-Nondeterministic Computations of Finite, Automata, and Pushdown Automata families and the effects of multiple counters. Welcome.
Okay, thank you very much. My talk is about the very fundamental machine models, finite automata and Pushdown automata. So everybody knows what they are, right? So this is the outline of one talk. This is about the finite and the Pushdown automata, but then I'm thinking about the family of those machines and non-uniform setting. Okay, I'm going to explain all the things later on. But then I'm going to talk about the effects of the multiple counters. So we are providing some counters to those basic machines and enhance their computational power. Okay, and I'm going to prove some inclusions and the classes of the classes solved by those machine models. Okay, so first now just briefly mention the history of those concepts. Vernon Lingers and Sudoku Sipser, they started talking about the family of the machines. And those machines solve the so-called promise problems. That's the family of the promise problems. And the machines taking the polynomial number of the states instead of just a fixed state, because we are talking about the families of machines. Oh, sorry, I forgot to turn on the microphone. Okay. Later on, there's a big time gap between the 1978 and the 2009, and Kapolsky sort of rediscovered the concept and starts talking about producing some results. And Pizzini and Yamakami, and also the Geffert and a couple other people, they actually started talking about exploring this notion and providing some more results. For example, I expanded the scope of the complexity classes, define all those machine models. So you introduce the counting finite automata and introducing some different kind of the machinery, right? And later, the very recently, I introduced the Pushdown automata into this model, the framework of the computational complexity theory. Okay, so now let me explain the models, right? I'm not really going to the detail of the finite state automata and Pushdown automata. Those are actually very known to the computer scientists. But then I'll just mention the abbreviation here. So 1NFA stands for the one-way non-deterministic finite automata. And the first letter 2 means the two-way hit loops. It actually moves back and forth, right? And this is about the Pushdown automata. So we will use an abbreviation of the 1NPDA for the one-way non-deterministic Pushdown automata and 2NPDA for the two-way version of the same Pushdown automata. So the head actually moves back and forth. Then we have a stack here. Okay, those are the basic model. I want to mention the push size. Push size is the maximum size of the string that is pushed into stack at any moment. Okay. All right. So we are dealing with state complexity. State complexity means that the number of the states used to build those machines, right? And for one single finite automaton, and the state complexity of it is written down here. So this refers to the number of the inner states used for this machine, right? Now now we are actually dealing with the family of the finite automata of the same type. Like, if you're using a deterministic machine, then all the machines in this family are deterministic. And if you're using a non-deterministic machine, then all the machines in the same family are non-deterministic. Okay. So in this particular case, the state complexity of this family of the machines is become a function in terms of the index n, right? So if each machine, for each machine, so this is the size of the internal states. Use this to build this machine, right? So each machine, depending on the index n, right? So this is the function in terms of n. Now, the family of the finite automata is called the polynomial size if the polynomial bound this function in terms of n. Okay, so we are allowed to use the polynomially many inner states to solve some problem. Okay. In the similar ways, we can define the Pushdown automata, the sort of the complexity of the Pushdown automata, but we can't simply use the same state complexity because because of the stack, we can actually reduce the number of the states considerably compared to the finite state automata. So we have to include somehow the size of the the stack alphabet used for the operation. So stack state complexity of the Pushdown automata is defined in this way. This is the multiplication of the size of internal states, inner states, and also the size of the strings up to the E. The E is the push size. Okay. And we generalize this stack state complexity to the family of the Pushdown automata by making this as a function. Okay? And we will use the same terminology, the polynomial size, for this family of the Pushdown automata by taking the forcing this some particular polynomial bounds the upper bound of this stack state complexity function. Okay. Oh, sorry. Yeah. All right. So now those families of the machine are used to solve problems. But now then the promise decision problems for molecules. The promise decision problem of the alphabet sigma is a pair of two sets. A and R are actually subset of the sigma star. So those are languages, right? And they are disjoint. So that's a requirement. Well, intuitively, you might think the element in A are accepted strings and element in R are rejected strings. Right? So the machine solved this pair, the promise decision problem, if for any x in A, if M the machine accepted, and all elements in R, M has to reject. But we don't care, whether machine stops, even if it stops or not, for the string that is not inside A and R. Those are the strings in A and R, union of the A and R are called the promise or valid. So we don't care about invalid strings. Okay. Now, the family of the machine is said to solve the family of promise decision problems if each machine, the nth machine, solves an nth problem in this family. Okay. So those are the basic setup. So now we will introduce the complexity classes. So 2D stands for the classical family. So this is the family of the promise problems solvable by polynomial size 2D FX, the deterministic finite automata times, right? But those machines are running in polynomial time. So 2D is the complexity class. But we are not expecting or allowing the probability, well, they're forcing the probability to be uniform. So you can take any possible probabilities, right? So 2D become non-uniform in the sense. So similarly, we defined 2N, 2U for the non-deterministic version and unambiguous finite state automata version. And the Pushdown automata, we just simply had PD to stand for the pushdown machine, right? 2D PD, 2N PD, 2U PD for the unambiguous pushdown automata. Okay, those are the machine, the complexity cluster. Those complexity clusters has a very complex, structure, similar to the standard complexity clusters. Okay. Those definitions are actually explained in a different paper. So if you are interested, maybe take a look. Okay, now we go back to our discussion. So the counter plays very specific, important roles in this talk. So the counter is the basically stack, but the alphabet, stack alphabet, contains only a single letter except the bottom one and one. Right? The counter automaton is the automaton equipped with this specific machine memory device counter. So usually we can actually add multiple counters to each machine. Right? And if you use the pushdown automata as the underlying model, then if you add counters, the machine is called counter pushdown automata. Okay. So now we use the two abbreviations, the 2NCTA for the non-deterministic, 2A non-deterministic counter automata. CTA is the counter automata, the abbreviation. And if you use the pushdown automata, the 2NPDCTA, it stands for the 2A non-deterministic pushdown automata. Those are just abbreviations. Okay, now we'll introduce, similar to the 2D, 2N, 2DPD, we add CTK, extra, the suffix to mention that we are using counters. And the K stands for the number of the counters, so that we are using the K counters instead of just fixed ones. Okay. Now, so this is actually the inclusion and the class result that we are going to present in this work, right? Starting with 2D and so on. Those blue-colored complexity classes are defined in terms of counters, and counter 1, 3, 4, and so on. Right? Okay, the power of the counters. Counter is a very powerful tool, so that for example, the complement class of the 2 and CTK is actually simulated by the machinery without using the complementation. So it seems to be the kind of closure and the complementation. But then you only have 4 counters. That is enough. So as the corollary, we'll get this result, right? Those results come from the two statements. First, the complementation class is actually simulated in increasing number of the counters. Then we reduce the number of the counters down to 4. Okay. The first one is the nice adaptation or expansion of the so-called inductive counting. Those guys proved use this new idea to prove that an NL is closed under complementation. Okay. Now we'll bound the size of the strings, right? Using the seeding notion. Okay. So all the promised, well, we don't care about the non-promised strings, right? So the non-promised strings have to be a size at most polynomially bounded. So in that case, we use an abbreviation poly. And if you use, sticking to the unary alphabet, right, as an input, then we will use an abbreviation of the unary. So we will use the this notation. 2n/poly means 2n restricted to polynomial seeding, so that all the inputs are bounded by polynomial size. Right? And 2n slash unary means that all inputs given to the machinery are actually unary. Right? Okay, so the counter can be eliminated if you use the polynomial seeding. So the theorem says exactly that. Right? As a corollary, this is a very nice, interesting thing. Right? If the deterministic case and sorry, I forgot the DC. Oh yeah, this is right. Okay, deterministic case and non-deterministic case with counters are exactly the same. So this is what we don't know yet, right? But if this is true, then well, here the non-deterministic log space complexity class is the same as the deterministic log space class with advice, the polynomial type advice. This is the notion of the Computations type advice notion. And similarly, we have the 2D PDCT CT3, so pushdown version of the first statement. If this is true, then the log DCFL, so this is the log space and the menu and closure of the DCFL, the deterministic CFL, the context-free languages, is the same as the non-deterministic one under Computations advice. Okay, so this is actually the picture we will get according to the theorems that I have shown before, right? Now I'm going to explain about the unary situation. Sorry, the complementation. Sorry, here. So I'm going to show this equality. Right? So if you use the polynomial seeding, then 2n and co-2n, so this is the complementation of the 2n complexity class, right? Complementation class. So this is the same, and also for the pushdown automata case, this is also true. The first result comes from the previous one, right? If you use counter, then this counter complexity class is closed under complementation. And we use polynomial seeding to get rid of counters. So you combine those things, then you will get the first one. The second one is similar. Okay. So now I'm going to discuss the unary input. Also unambiguity of the machines. Okay. If you use an unambiguous machine, so that's defined 2u, right? 2u is the same as 2n if you use the polynomial size promised input, right? The same is true for the pushdown case. Those results are a little more complex, so we'll introduce and parameterize the complexity class, and then so we have to deal with those parameters, size parameters. Now, finally, now just show some challenging of the questions. The first one is we have talked about 2n, 2n, 2u, 2n, co-2n. Those are actually exactly the same if you use the unary input. But we do not know whether these results can be extended to a pushdown automaton level, right? So this is still unknown. The second one is so far we proved this kind of statement. Well, this kind of statement under the condition like using the unary input or polynomial seeding, but without any condition. The whole entire complexity classes are exactly the same or not. I don't know. Because that actually implies some collapse in the standard complexity classes. Right? The last one is the same kind of thing holds for pushdown automata situation. So overall, the studying the finite state automata or the pushdown automata, people tend to think those are actually slightly different from the Turing machine model, like a standard complexity classes and P, NP, and so on, right? But actually, if you have this setting, right, there is the connection. So if you really tackle the finite state and the pushdown automata and solve some question, something like this one, right, that have a direct implication to the collapse in the standard complexity classes. Okay, well, thank you very much for listening, and I'm happy to take your questions.
Any questions? Please.
Can you give an example of a problem in these classes?
Oh, I see. For example, if you think about it, then say something like an A to the N, B to the N, for example, right? So that's just a very simple language, right? So you can expand. This one is actually the family or series of the problems, right? Those are actually solvable in 2D, for example.
And with counters?
Pardon me?
When you have counters, for example, when
Oh, the counters. Okay. For counters, I think I listed something in the paper, but I completely forgot this. Sorry.
I would say.
Yeah. Yeah. But then if you're actually looking at those situations, right? Then the languages are quite simple compared to the standard complexity class like P, N, B, and so on, right? So that's why then it is very interesting, right? The problem is simple, so you have some idea on how to solve those things, and that actually have a direct connection to the more complex complexity classes.
Let's take other questions.
Thank you.
Okay, thank you very much. Hello, everyone. I'm staying in Hong Kong to attend a conference, international conference, so-called TAMC, TAMC 2024. It's May, and we have a very sunny days. The first couple of days, and I had the little bit showers in the afternoon. But after that, then every day is really sunny, and the conference is over now. I gave my public talk this morning, and today is the last day of the conference. Conference only takes only 3 days, so quite short and condensed. For example, the first day, we started the invited talk 9 o'clock in the morning, and all the contributed talks ended at 6 o'clock. I skipped some of the talks to go to the post office, which is a little bit away from the university and also from my hotel. I'm staying in Automata hotel, which is closer to the university. One of the interesting things about the university here is that I got the QR code to get into on campus, right? So there is the kind of guards checking out all the influx of the people. So without any the QR code, the people will not be let in. Okay. So my flight back to Fukui, Japan is set on tomorrow morning, 8 o'clock in the morning. So I have to get to the airport probably 2 hours earlier than that,
but the problem is that the train. Well, I'm planning to take the so-called Airport Express train, which begins in the morning at 5:55. So probably without taking the early train, probably it's now miss my flight at 8 o'clock. So I have to get up early, something like probably 4 o'clock in the morning, and I have to pack up everything and then walk to the nearest express train. Okay, so hope to see you sometime.